Hello, accelerated chemistry students. This is Ms. Krista Foley, and this is your Chapter 13, Section 3 video notes all over the nature of solids. So let's talk about solid models. So the general properties of solids reflect the orderly arrangement of their particles and the fixed location of their particles. In most solids, the atoms, ions, or molecules are held tightly together. Solids are dense and not easy to compress. Because the particles in solids tend to vibrate about fixed points, solids do not flow. But when you heat a solid, its particles vibrate more rapidly as their kinetic energy increases. The melting point is the temperature at which a solid changes into a liquid. At this temperature, the disruptive vibrations of the particles are strong enough to overcome the attraction that holds them in fixed positions. So the freezing point is the temperature at which the liquid changes into a solid. The melting and freezing point of the substances are at the same temperature. So when we're going back and forth between a solid and a liquid and solid, they are occurring at the same temperature. It's just whether or not you are heating the particles or whether or not you are cooling them. Are they gaining kinetic energy or are they losing kinetic energy? At that temperature, the liquid and solid phases are in equilibrium. In general, ionic solids have high melting points because they have relatively strong forces holding them together, ionic bonds. Sodium chloride is an ionic compound and has a rather high melting point of 801 degrees Celsius. Molecular solids have a relatively low melting point, like hydrogen chloride, a molecular compound, and it melts at negative 112 degrees Celsius. And that is because molecular solids that have covalent bonds, have weak interactions between them. In a crystal, the particles are arranged in an orderly, repeating three-dimensional pattern called a crystal lattice. The shape of a crystal reflects the arrangement of the particles within the solid. So if we were to look at sodium chloride, the sodium ions and the chloride ions are closely packed in a regular array. The ions vibrate about fixed points in the crystal. Crystal systems. So now let's talk about how crystals are classified into 7 groups or crystal systems. When we look at these crystal systems, you're not going to have to know these. These are for a higher level chemistry class, but I just wanted to let you know that there are definite different arrangements, and these should look familiar from a geometry class that you've taken in your past. We're going to label the edges A, B, and C, and the angles alpha, beta, and gamma. And as you can see, all of these look different, and that's because all of them have different arrangements of their sides. And in our case, every corner or every intersection is going to be where an atom would be. There are 7 crystal systems, differ in terms of the angles between the faces and the number of edges of equal length in each face. So the shape of the crystal depends on the arrangement of the particles within it. The smallest group of particles within a crystal that retain the geometric shape of the crystal is known as a unit cell. A crystal lattice is a repeating array of any one of 14 kinds of unit cells. Each crystal system then can be composed of 1 or 4 types of unit cells. So the figure below shows the 3 kinds of unit cells that can make up a cubic crystal system. So we have a simple cubic, a body-centered cubic, or a face-centered cubic. Basically, all that means is where are your atoms being placed? Are they placed on the corners? Are they placed on the corners with one in the middle? Or are they placed on all 4 corners of the cube and then in the center of each face of the cube? Now let's talk about allotropes. Some substances can exist in more than one form. Diamond is one crystalline form of carbon, a different one is graphite, and the third is called Buckminster fullerene. And this is what they all look like. In a diamond, each carbon atom in the interior of the diamond is strongly bonded to 4 others. That's why diamond is so strong. Graphite, on the other hand, is linked with widely spaced layers of hexagonal carbon rings. And then in Buckminster fullerenes, you have 60 carbons that form a hollow sphere. The way these carbons bond in all 3 of these allotropes give all 3 of these structures of carbon different properties. So the physical properties of diamond, graphite, and the fullerenes are quite different. Diamond has a very high density and is very hard. Graphite is a relatively low density and is soft and slippery. And the hollow cages of fullerene give them strength and rigidity. Diamond, graphite, and fullerenes are crystalline allotropes of carbon, Allotropes, by definition, are two or more different molecular forms of the same element in the same physical state. And then, although allotropes are composed of atoms of the different element, they have different properties because their structures are different. So there's only a few elements have allotropes. In addition to carbon, there are phosphorus, sulfur, oxygen, boron, and antimony allotropes. Now let's talk about non-crystalline solids. So not all solids are crystalline in form. Some form solids are amorphous. An amorphous solid lacks an ordered internal structure. Rubber, plastic, asphalt are amorphous solids. Their atoms are randomly arranged. And other examples of amorphous solids are glasses. A glass is a transparent fusion product of inorganic substances that have cooled to a rigid state without crystallizing. Glasses are sometimes called supercooled liquids. And the irregular internal structure are intermediate between those of a crystalline solid and those of a free-flowing liquid. And that is the end of your Chapter 13, Section 3 notes. And as always, all the information on these Google Slides has been acquired and adapted from Pearson Chemistry's 2012 edition of the Textbooks Resources CD and pearsonchem.com. Thank you so much. Have a good night.